So we will do a couple of examples today, and first of all we'll start off with comparing the mean to a value. So the average age for first marriages for men in New Zealand is 28.9. Did you know that? I looked it up on the Statistics New Zealand website, which has all sorts of interesting little facts like that. And in the questionnaire, you students were asked what you thought was the ideal age for a person to marry. And so what was the result different from 28.9? Because is it that people want to get married younger than that, but it actually happens at 28.9, or do they want it older, but they get married before they thought they would, or whatever? I thought 28.9 was quite old actually, but yeah, for the average age. So our null hypothesis, and I'll just make sure I don't confuse myself and everybody else on this. Okay, so is that the mean ideal age to marry is so our null hypothesis is that it is the same. We're saying that what people thought was the ideal age is the same as this number 28.9. Okay, and an alternative hypothesis, and we're just talking about the men here, so I'll just say I only looked at the men's data. So here we've got the alternative hypothesis. Can anybody tell me what the alternative will be? Okay, basically you rewrite it exactly the same, only we change is equal to is different from. So the mean ideal age to marry is different from 28.9. Okay, so just straight off, is that a one-tailed or a two-tailed test? Hands up if you think it is one-tailed. Hands up if you think it is two-tailed. Okay, that's good, it is two-tailed. Does anybody want to tell me why it's two-tailed? What's the key word? Keyword is different. Okay, so it's saying it's different from 28.9. If it said it was greater than 28.9, then it would have been a one-tailed test. Okay, so choose a level of significance. What do we normally choose? Yeah? 0.05. So let's just choose 0.05, because why should we do anything else? Okay, so now we collect the data. So we asked 102 male students what they thought the ideal age to marry was. Okay, so I know I'm actually dealing about two different things. The 28.9 is the average age, and we're talking about ideal age, and that was the average age for males, whereas we were just asking males what the average age is. So there are some differences here. I'm not going to do this bit yet, because first of all we need to calculate the p-value. Okay, now what we want to do is we're looking at what is the probability of getting a mean of 26.8. Now where the heck did that come from? Okay, I'll just check something. Okay, if we look at our data here, okay, so we do our calculations, and this is what comes from the data on page 5, and you can see there's this number 26.8. So that's the mean of the sample. So the sample was 102 students from this class. Okay, so what is the probability of getting that mean, 26.8, from a sample of 102 students if the actual mean of the population is 28.9? Okay, so you've got 26.8, 28.9. Does that look as if it's significantly different? Okay, well, there are two things that we would say to answer that. One is, it depends on how big our sample is. If we took a sample of 500,000, clearly that's different. If we took a sample of 10, you go, well, it could have just been that we got the people who put down smaller numbers or something like that. And it also depends on how varied the data is. If there's a lot of variation, then this difference of 2.1 is not very much. But if the values are pretty close together, 2.1 is a big difference. So this is what we're looking at here. So the formula is similar to the one that we used in calculating confidence intervals. And what you do is you find this t statistic, and you do that by the sample mean, which was 26.8, minus the hypothesized mean. See, it's got a Greek letter. That's the Greek letter mu, which means the population mean or the hypothesized mean, which was 28.9. Our sample standard deviation, that's telling us how spread out the data is in the sample, because we don't actually know how spread out the data is in the population. And then the square root of n, which is our sample size, because as we get a bigger sample, then we will get more and more evidence, and so our t-value will actually decrease. So it will increase, sorry. The distribution of the mean. Now, this is a tricky idea, and don't worry if you don't totally get it, but I want to put it in here because some of you, if you're carrying on with statistics, need to understand this principle of the sampling distribution. Having said that, I think I only got it a few years ago when I started teaching it because it's a weird idea. Okay, so we're talking about the distribution of the mean. We're not talking about how spread out all of the ages were that people wrote down. What we're talking about is how spread out are the means that we would get from the population. If we took lots and lots of samples of 102, how spread out would the means be? And that's called the sampling distribution. Now, it has a mean of the hypothesized mean, so that's what we do, and a standard deviation which is related to the sample of the standard deviation. And if we knew the standard deviation, we could use it, but we don't. So we use, okay, now, if we knew this value here, we could use the normal distribution, because we make this assumption that means always follow a normal distribution. But we don't know this, because if we knew this, we'd know a whole lot of other things too, and so it's absolutely pointless. And a lot of courses, they teach you how to do it if you know what that is using Z, and as you never do, I always think that's a really dumb thing to be teaching you. So we just skip that whole bit and say, look, you never know what the standard deviation is for the population, because if you did, you'd know the mean. So instead, we use this sample standard deviation, but we have to use what's called a student's t or a t distribution. Okay, now most of this you don't even need to worry about because Excel takes care of it, but I like you to have some idea of what's going on as well.